welcome back to another episode from High Water Studio. Today we're going to be talking about groundwater elevations. This is a topic that most of your junior engineers, your engineers that are new to a company, your EITs that are just starting out, trying to make their way, are going to be probably pretty familiar with, or going to be becoming familiar with. Because typically that is one of the tasks that we typically require of our new engineers. And, it can be a good task to be a part of because it gets you out in the field, it gets your eyes on the site, gets you familiar with what's going on. So it actually can be a really good experience, in my opinion at least. So, but how do we do this? What is all this? What does it mean? So we're going to be talking about three main topics today. We're going to be talking about how to measure groundwater elevations in a more theoretical sense. We're not actually going to be doing this physically today. That'll be a follow-up video. We're going to be looking at the difference between vadose, saturated, and confined zones, different layers, and how these interact within the whole hydrology of the Earth. And thirdly, defining groundwater contours and piezometric surfaces, and go through a quick example, real simple example, of how to actually calculate groundwater surfaces and draw some simple groundwater contours. In a different video, in part 2, we're actually going to go out into the field, measure some groundwater elevations, and actually take some samples. So that should be a lot of fun. I'm working on scheduling that right now. Let's close that one out. So, okay, let's talk about this probably overly busy diagram here for groundwater elevations. So, where to start? Basically, this is our ground surface, all right? And so imagine this is like a street, this is a curb, here's our ground surface. This is typical, at least for the fields that I work in. You're going to have a reference point somewhere, maybe in the curb, that's going to be a known elevation that you can work off of. And we're going to use that as we try to determine what these different elevations are and how they relate to each other. You always have to have a known point to begin with if you really want to do proper contours of any kind, really. So moving on from that, I guess the next thing would be maybe what these are. These are not drawn to scale, but these are well nest. So a lot of times, or at least some of the times, if you're trying to get a profile, a deep profile, a really broad view of what's happening within your area, then you're probably going to nest some wells together. And that basically just means you're going to put wells right next to each other that are going to be at different depths, right? Or in different zones. So in this case, we have two wells within one nest, and one is going to be in the saturated zone, and one is going to be in the confined zone. And what is the difference here? Well, from the ground surface going down to the water table, this is what's known as the vadose zone, or the unsaturated zone. And basically that means your pore volumes, your pore voids, or the empty space between soil particles, are not fully saturated. So you don't have as much water as you possibly could have, right? It's not fully saturated. And once you reach full saturation, that is your water table, or it's more often defined as when the pressure is equal to atmospheric, because you actually do get negative pressure above the water table in your capillary fringe that pulls water up into the vadose zone. And you get this kind of smear zone where water is being sucked up into the voids because of negative pressure. And you've maybe seen this, or you could see this, if you take a glass of water, you drop a straw down into it, and if you look, probably the straw is going to have water a little bit higher than the water surface around it, and that is the capillary effect. Okay, so that's capillary fringe, and usually what you're going to try to do within, below the vadose zone, you have your saturated zone. Your saturated zone is your fully saturated void spaces, beginning when you have the water table, you have atmospheric pressure, and typically, definitely, what you want to do is have a screen zone that intercepts the water table here. So typically, you'll have from what I've seen, they're often 10-foot screen zones. They're like slotted, they're PVC usually, cut with slots to allow water in, keep the aquifer material out, and then you'll have your risers rising up above that so that you can, access that water table. And then below that, if you want to go into deeper zones, you have your confined zone. And this is where things get kind of weird, basically. And usually, well, always, this would be when you have it below, when you have water below a confining layer, which I've designated here. And this is usually a clay layer or some kind of, very low permeability layer, usually a clay layer. And what happens is this clay layer is impermeable, so it basically separates everything above it from everything below it. And you can have it, going up the side of a mountain. You can have very high water tables that come down and basically pressurize this confined zone. So when you put a well down into a confined zone, you can have a water head of any elevation, basically. It can be anything. It can even come up and basically break above the surface and basically flow freely onto the surface. That's known as an artesian or artesian well. So in this case, we have our water surface, our waterhead surface, marked here, and that is known as the piezometric surface. So this sort of imaginary line of where water would flow to if it were free to do so is the piezometric surface. All right, well, I think I've almost defined everything except for how to actually do any of this. Okay, so that's what all this stuff is. What do we do with it? All right, so what we would do if you wanted to actually get any of these values is you're going to need, of course, to start with a reference point. You're going to call in a survey crew after the wells are installed, and they're going to come in and measure the elevation of your risers. And in a nested well, maybe they would just do the casing. I think that's probably a bad idea. I would probably do every riser because, for one thing, in this example here, a lot of times these guys that come in and put the risers in, they just kind of cut it off with a hacksaw, and a lot of times they cut it off at an angle. That's just kind of what happens. And so by convention, at least from everything I've ever heard, you always measure on the highest side of the riser. And it's kind of important that you at least have some kind of convention, because if you move around, then it's going to obviously cause some kind of, inconsistencies in your measurements. So measure from the highest point, and always measure from the highest point. And then least from then you will have some kind of consistency in your measurements. So what we'll do is measure our riser, and then from there we put a water level measurement tape, and there's different kinds, and we're going to show that in the next video. But basically, we're going to measure down from the riser, the top of the riser, to the water level surface. And it really doesn't matter if you're talking about saturated zone or from the confined layer, measuring the piezometric surface, because it's going to be more or less the same inside of a well. Okay. See how we doing on time. 8 minutes, 9 minutes, not too bad. All right, so a quick little example of like, how do we apply this stuff? How do you do a contour map once you have gone out and made these measurements? All right, so we have wells A, B, C, and these are just one well. They're not nested wells. We're just going to look at water table elevations just to keep it simple. I mean, it's basically all the same thing. But in this case, we have a reference point at 100 units of your choice. I'm going to say feet. You can say whatever you want. A is 10 feet below our reference point, so it's at 90. B is 20 feet below reference point, so it's going to be at 80. And C is 25 feet below reference point, so of course it is at 75. Our water table at A is 10 feet below, so it's going to be at 80. Our water table at B is also 10 feet below, so it's going to be at 70. And our water table at C is 5 feet below, so it's going to be at 70 as well. And so what happens here is you wind up getting these contour lines. Now, we only have so much data to work from, obviously, with only 3 points. And this is kind of typical. It's hard to, imagine this from a plan view, but a lot of times you'll have like, if you imagine this kind of ground level where you might have a hill here coming down to a slope, but then you'll have one level groundwater, going between those 2 points. If that makes sense, I don't know. But once you get your measurements, then it should make sense, because between these points, you're going to have the same elevation. So in this case, you have, well, really the only conclusion you can make is that you have a straight line contour between those 2 points. And relative to that, you have a straight line contour at 80 feet at point A. Now you can also interpolate anything between those 2 points. Of course, it's going to be straight lines. But for example, if you wanted 75 feet, it would just be, equal distance between A and B. The only real other thing is to mark the groundwater flow direction, which of course is going to be from high to low, high gradient to low gradient. And that concludes our lecture for today. I appreciate you joining us today for our episode on groundwater elevations. I'm sure you've seen a lot of YouTube videos before, so you know how this works. If you enjoyed the video, and if you want to help out the channel in any way, the best help we can get is some subscriptions or a comment. We definitely appreciate it. It really helps us a lot. Thank you very much. No matter what you decide to do, we appreciate you taking time to watch our video. Thank you.